Ladies and gentlemen, welcome to the first talk of this session. The speaker is Fedor Smirnov from CNRS. He is an expert in integrable quantum field theory and is going to talk on a space of integrable quantum field theories for the next hour. Please join me in welcoming Fedor Smirnov.
Thank you. So this is a joint, I will be talking about joint work with Alexander Zamolodchikov. And so I would like to thank CBS for recognizing our paper with this Field of Science Award. So, so let me begin. Let's see. Like that. Okay. So I'll be talking about two-dimensional quantum field theory in Euclidean space. And so actually, more or less all my life, I worked on two-dimensional quantum field theory. So, and this is a kind of trap because you have a field theory with some exact results, and so which is quite unusual. And so it is so amazing that you continue working on that. And one of the an excuse for me I find in the fact that my colleague Zamolodchikov is doing more or less the same thing, and I admire him very much. And so probably there is something in that. Yes. Right. So now to be precise, so we have two-dimensional space. So and we have to distinguish this chiral z bar from this z, and so this is integrable model, which means that there is an infinite number of local densities which satisfy this continuity equations, and so S here is some infinite set, so it can depend on particular model. So now these are our notations, but so for the components of the energy momentum tensor, one usually uses TT bar and theta. Theta is trace of the energy momentum tensor, and so then so these are local densities, and so here are conserved charges for these local densities. So which produce the local integrals of motion. Oops, no, not this way. Good. So to be precise, I will consider the geometry of cylinder, yes, so and then my integrals of motion are integrals around these big cycles. But in addition, so I insert one or several, I'm mostly talking about one, local operators here, and then there are small cycles. And so for this, for integrals, the small cycles, I use this lattice, yes, so of course, yes. In this geometry, they can be, you can push this cycle to the difference of these two, but so it is convenient to use this because, so for example, if you, so this is because my integral is from local density, but so if you would have, so this geometry also works for Virasoro descendants and things like that. Yeah. So now this the integrals they commute, and so it's easy to see that this requirement of commutativity of integrals is equivalent to these equations, to existence of A and B such that these equations are satisfied. So for some local operators A and B. And so let me stress that I return to my picture, that the difference between these guys, so these are integrals of motion, while these ones, they create some descendants of the field which I put here. Yes, so the descendants are, so this is some part of descendants, actually a tiny part. There will be, there are much more. I will talk about this. So these operators I and I bar can be diagonalized, and so but while these guys, as I said, produce some descendants, which means new local fields starting from given one. And so one more thing is that I will this direction over this circle direction I will always call Matsubara for some historical reason. So if you hear this word, so don't be afraid. So now we want to introduce some interesting local operators starting from these components of the local densities. Namely, consider such a combination for two space, for two separated points, z and z bar, z and z prime. And so then I want to prove that in the limit, when z goes to z bar, so this thing creates some operator plus derivative terms. Actually, derivative terms may be of something which is divergent, but so like usually in conform of in the limit. But usually, like in quantum field theory, you throw away all the divergent pieces. So, which means that this combination defines me a new local operator, which is a composite field. So, and how to prove it? So, we first consider this derivative with respect to z bar and obtain something like that. But then there is a operator product expansion. Yes, so that the product of two operators is given by actually convergent series with some structural constants and with series over all the local operators. So, and then these guys, this derivative z plus dz plus dz prime, they go through these ones because they depends on some, this depends on difference, and go up to these operators and differentiate them. And so in that way, I prove that indeed, so there is some kind of constant term and then derivative terms, because this derivatives here, this derivatives, they fall to these operators. And so this is how I prove the existence of this limit. Yes, and similarly for another calculator. And this is how I prove, as I said, the existence of this limit. So I proved that there is this composite operator here. And just to be clear about the meaning of this operator. So suppose you are close to ultraviolet limit, yes, so then this thing is much more important, much more singular than this thing, because just because of scaling dimensions. And so in the conformal limit, I am talking just about the product of these two operators. That's why it's often called TT bar or something like that. Yes, so TT bar is when S is equal to 1, then this is the why minus here? Should be plus here. Sorry. This is copy paste. Okay. So yeah, so this I repeat, this is this operator plus derivative term, and so it is an consequence of this is that it means that if I compute some expectation value of this operator xs because of the previous formula, because of this formula, it is just a determinant of this type which is constructed out of expectation values of every of these operators. So in particular for the simplest case s equal to 1. So this is a formula, this is this formula which was discovered by Zamolodchikov, and later on we will see that this formula, already here we see that this formula allows significant generalization, but later on we will see for particular example of integral model that it allows rather far-reaching generalization. So which way I go? Yes. So now the next thing is that so I do now some preparations in order to prove that if I perturb my field theory by this operators xs, then I still obtain an integral model. So let me. So this is just some preparation for this to prove this state. So first of all, I want to show that this is applied to xs is a total derivative. So consider now this. Consider 2 points and integral cycle around 2 points. Yes. So and then the action of this cycle, the integral of the cycle will denote by delta I. Delta is kind of for co-multiplication. I don't know why I call it this way. So now I consider this expression, and it splits in 2 parts. So, and the first part is important, so which is like that. And once again, I proceed with my tricks. So I apply this. I proceed with my tricks. So which use this. So this expression can be rewritten as this kind of derivative. And once again, so because of OPE, so this goes directly to these operators, and this is how I prove that this belongs to, that this is a total derivative. Yes. So now consider the correlation function. I have some insertion, some operator O, and then this guy here. So this insertion can be of this form, several points, for example, I allow. But this doesn't matter because and I deform my action, adding some infinity. Okay, so you know what I want to say. So this thing I deform like that. So at this xs, and then the format of C looks like that. So, and I am interested in the first term here. And so, and so I lower the path. So my action is original action plus integral of this x over the plane. Yes, so, and I lower this path with integral. I put it downstairs. Yes, and so then the integral over w is given by this integral over some domain d plus an integral over domain d bar, which will, so by completion, which will not be important for me. So I'm interested in the integral with this d. And so I assume that all the insertions are outside. And then what am I saying? Yeah, what am I? Where I'm going? Yes. So yes. So this is my geometry. Yes. So now it has been proven that this thing is a total derivative, and then if I act by this my operator is small on this x, so I obtain something like that. Yes, but for some because it's the total derivative. So for some operators, local operators, t hat and theta hat, but then the integral over d by Stokes theorem gives like that, becomes like that. And this means simply that I again have my continuity equations if I just change the definitions of my t and theta this way. So, and so we obtain, by this deformation formula, we obtain an integrable model again. And so starting with the given one. And actually, it's not very difficult to argue. So it will be clear later that it's more or less the only possible construction. Definition of what? Where? Oh, yeah. Action, yes. Yes. Sorry, I am not sure that this thing must be downstairs. Probably I just added this. So yes, it's so now to be more down to the earth and to have an example, I will consider in some details here the Sine-Gordon model. Sine-Gordon model has this action, and in addition, I will consider what I will call the primary field by analogy with conformance, but I will talk about this here. But anyway, so these are called primary fields, and so it is convenient to use this to parameterize the coupling constant in this way, and I will use the modified energy momentum tensor. So, but this is not very important here, but somehow convenient for me, because the trace of this modified energy momentum of this component of this modified energy momentum tensor is given not but by cosine just by exponent, by primary field itself. And so this is an integrable model, and we have an infinite set of local integrals of motion with all odd spins. So now, if I consider the expectation value of, so not even here, but in any case, so if I consider the expectation value on my cylinder, which I had from the very beginning, so probably let me return to the scene. Oops, not this way. The expectation value of this descendant is, of course, given by the difference of integrals of motion here and here, because I just deformed the quantum. So that's why the expectation values of this descendants created by the local integrals of motion are easy to calculate, but they are of no interest actually. So, in fact, if we want to have a description of complete space of local fields in the theory, we need something more, not only descendants of local integrals of motion, but something else. And this something else, so it took some time to figure out what it is, and so it is described. It is a work of several years by Jim Bamivas and myself, both also years. And so the result is the following: that so we have, in addition to this descendants of local integrals of motion, we have on this space we have action of some fermionic operators. So there are two fermions, so psi, or how many? Four probably. Psi and he and psi bar and he bar, so altogether four. And so the only non-trivial commutation relations are here. So all the rest of them commute. And so then the primary field plays the role of vacuum. So it is annihilated by 1/2 of every of these fermions. And so then the descendants, the local operators, are created by action of these guys, with the only restriction that the action of psi and, let me see, psi and psi bar must be the same as the action of number of psi and psi bar together must be the same as the number of he and he bar. And so then the expectation value of these guys, so with any boundary condition, integral boundary condition, which I can put to the left and to the right of my cylinder. So they are, yes, alpha is so let me see. Alpha is somewhere. So sorry, alpha is here. No, they don't. They don't. They do not depend on. So alpha is hidden here. Yeah. It's computation relation. Yes, they depend. Yes, that's it. That's right. No, actually, yes. I'm sorry. They of course depend. Their definition depend. But what I want to say is that, as I will explain soon, so this picture, of course, in the ultraviolet limit. So this picture must correspond to what you have with the usual Virasoro descendants, right? Because in the ultraviolet limit, you go back to the conformal field theory. And then actually these guys here, you see, so this number of psi's here and number of chi here are not necessarily the same. And so this will be not only Virasoro descendants of the field phi alpha, but of all the shifted, of the field shifted like that. Why I put I here? So this is another story. So, yes. Right. So now, if I consider the limit of, I have my cylinder, and I consider the limit when the radius of the cylinder goes to 0. Yes, so then I have such a, it's easy to see that I have such limits, yes, and theta is much milder than this guy. So I got, so this trace of energy moment tensor disappears, and I am to my usual conformal field series of that. And so then I define, in this limit, I can define the Virasoro descendants, so central change like that. I can define the Virasoro descendants and then start to create the Virasoro generators and start to create my descendants by Virasoro now. And so, first of all, in this limit, so it can be, I can write explicit formula which express my fermionic descendants through Virasoro descendants. So they are the same. And so, I mean, they are the same, so there are some formulas. But also, there is an important thing that if I consider the Sine-Gordon model as perturbation, this time as normal relevant perturbation of the conformal field theory, yes? So then there is this arbitrary parameter alpha, and it's easy to see that I can establish one-to-one correspondence between the local operators in perturbed theory and the local operators in conformal field theory, and this is without ambiguity because all the finite quantity terms that you can imagine, I throw them away by dimensional considerations. So that's why this is a very important point, that I will still use the same thing, the same fermions which are defined for any Sine-Gordon model, yes, not only for ultraviolet limit, but so I understand them as the ones obtained from the ultraviolet limit by this unique procedure. So, and then, so this is what is written here, so that this, I have this space of descendants of this shifted operators. And I claim that this space is the same as the space created by my fermions. And so this was explained in this works. And so especially I would say that this work is very kind of dear to my heart. Okay, so now why these things are interesting? Because so there is I had up to now I considered the case of arbitrary alpha. So now if alpha is equal to 0, yes, so then I have some additional properties of this fermions. So there is an operator Q. There are several things, but so I describe only one of them. So this operator Q, which I defined like this, yes, so it is with local integrals and fermions. And so I claim that acting on something, you see, there are annihilation operators here. So something must contain additional creation operator. But so this is a formal thing. So then acting by this operator on any other operator, I obtain gives 0. So this gives me in particular this relation, which is nothing for me but the continuity equation, which I have from the very beginning, because so you see this I1 bar, and so this is my local density must be applied to 1 like here. These are my local densities described in terms of my fermions. And so this agrees with the following identification between the action of fermions and local densities. But now, if I consider something more interesting, so first of all, this my operator XS, then because so let's see once again. So I had the conformal limit, yes, and in the conformal limit, this operator is just a product of 2 local densities, because for 2 chiralities they are just absolutely independent, right? But then I raise it to the Sine-Gordon quantum field theory, and then I said that I can do it with my fermions, and so then it cannot be anything by that. Yes, so this my operator XS must be like that. And so let's consider the simplest example of application of this fermion. So now this expectation value here is given by according to my fermionic formula, is given by this determinant. And so when alpha is equal to 1, this gives me the expectation value which I had before. But so actually, on the other hand, so I have much more formulas, because I had determinants of any size. So all the any expectation values in my fermionic basis are determinants of one-dimensional one, of the simplest ones. So this is the important property. Okay, so let's consider one more interesting example for this alpha equal to 0 case. If I consider such an operator, and I act once again by my So I obtain acting by operator Q, I obtain the following equation, which is actually which clarifies. So I have this formula that the derivative of xs is equal to sum of two total derivatives. So here with sum t hat and theta hat. So this gives me exactly this t hat and theta hats. And I can exercise with that a lot. And so now I come to, since we're talking about Saint Gordon, I come to another important thing, which is, yes, a question? Yes, yes. Sorry? Ah, chi minus s. So, yes, so this is, no, this is for chi minus s. So, I don't know how to say it, but so, have so you have two fermions, yes. So then so there is some of them are annihilation operators, some of them are creation operators. Creation operators create operators of spin S. Annihilation operators annihilate everybody, the primary field. So now, how do I understand? So I have this perturbations now of the integrable model, and I want to understand, so what do they do for, what is the effect of this perturbation for the physically relevant objects? And physically relevant objects, the most important is the S matrix, yes? So, and I want to understand, so after the perturbation, how the S matrix changed. So, and for this, I have to say a few words about so how I compute the form factors in integrable models. So form factor is a matrix element between of given local operator between vacuum and some excited state. And so excited state, so I mean the state with I'm talking here only about solitons. The space with rapidities beta 1, beta 2n. And so I don't want to go into details here, just a few words. So that, first of all, it's convenient to introduce this Gothic letters for rapidities and for some variables sigma, which are integration variables. They will be either Gothic letters for these exponents or just big letters for these exponents. And then the form factors are given by in terms of such integrals. So Meline transforms of some such function, which is the most important function for me in this thing. And this function, so I don't write the explicit expression for the function, but the important thing is the function. When I shift this sigma by 2 pi I, it produces me a ratio of two polynomials of this variable, which likes another period, and vice versa. Which I check with the variables by the shift which this variable likes. It produces me the some ratio of polynomials which it dislikes, right? Which Q? Ah, Q. Yeah. Q. There are two Q's here. So where is the choke? Yes, you're right. There are two Q's here. Like that. Right. So probably yes. So for if the so I have this milling transforms with this parameter alpha here, yes, and so then the pairing between these two polynomials is defined like this milling transform at this shifted point, and so then for if I take antisymmetric products of these guys and these guys, then I define the pairing of these two by these determinants, and then I can make the linear combinations of this. And so the only important thing here is that there are polynomials like that. So whatever the definition is, so so never mind. There are some polynomials, and so then if I want to compute now I compute. So the advantage of this fermionic picture is that I can compute whatever I want, not only say expectation values in finite volume, but I can compute the matrix elements in infinite volume, whatever I want. And so then this kind of polynomials, they give me, when I develop them in Z and X, they give me the descendants for the form factors, they give me the descendants of local operators. So, and so I have formulas like that, so that so these are the formulas for the form factors. But the only important, so I would like, I don't want to go into details here, but so the important thing is that if I compute the form factors of my operators XS using all this machinery, then the result is like that. So there are total derivatives. So these guys, of course, correspond to total derivative. Yes, with respect to, I mean, so if you go to the Fourier transform, so on a mass shell, this thing vanish, right? If I consider, so there is a crossing symmetry, and I can consider matrix elements not from vacuum to something, but from something to something. So this is easiest thing to do. But so anyway, so the important thing is that these things vanish on a mass shell with one. But this is not so simple actually, because so these functions g and g bar, they contain some singularities. And so one has to be careful with the singularities. And generally, so I can introduce some regularization to argue that these singularities after regularization, they disappear with one notable exception. So if I have here, if I will have the 4 particles here, I mean n equal to 2, this guy is very special because for this one, the singularities do not cancel. So I cannot I cannot introduce, so they are more or less opposite, they are just cancelled. So I cannot introduce such a procedure which get rid of them. And this is good because so what does it mean? So I want to show that after the perturbation, I get again an integrable model. What does it mean from the point of view of scattering? It means that first of all, there is no multiple creation. So that if I would have 2 particles goes to 10 particles, so this cannot be an integrable model. So the only case when the model is integral is when I don't have anything but 2 to 2, right? Otherwise, I break the factorization of scattering, and so the model is not integrable. And this corresponds exactly to what I said, because so that this after regularization, all the form factors all the form factors with more than 4 particles on shell, they disappear, and for 4 particles, I get some explicit expressions. And so now what exactly I get? So I have to say 2 words about CDD multipliers. So if you have, so this is an old story in the S matrix theory that unfortunately, so the S matrix is not uniquely defined. Unfortunately, or fortunately, I don't know. So it depends on point of view. So you can multiply it by some multipliers which will not break unitarity, crossing symmetry, nothing, and so, but still, so even if you are given some S matrix, so then you can always, I mean, the idea is that you have some unique S matrix and you reproduce your theory from this unique S matrix has this problem that the S matrix is never unique because there are CDD multipliers. So in our case, the CDD multipliers, so I have this Sine-Gordon matrix, say 2 by 2, and I multiply it by some function phi, which satisfies this equation and doesn't have poles on a physical strip, and this is the CDD multiplier. So, and then since so the corrections to the S matrix are obviously given by the 4 factors of 2 to 2 on the diagonal of my operator XS, I can compute everything very explicitly, and the result of the computation is that what will happen is that the matrix elements between 2 on the diagonal, yes, between the same states. So, and continuity means the procedure which I explained that you have to regularize somehow, that for 2 to 2 scattering, it is given by something, and for other scatterings, it vanishes, and that's why. So the only effect of the perturbation to my action by operator X is here. I mean, not by my operation, but many operators. So is here. So it is a CDD multiplier. So I took my S matrix and I multiplied by CDD multipliers. And up to now, everything goes very smoothly. But so then the serious questions arise which require some computation. And so it seems that this perturbations, so without very much, that they exist as ultraviolet complete quantum field theories in the sense that they does not seem to correspond to any fixed point and to any relevant perturbation starting from some fixed point. And so then the study of corresponding renormalization group trajectory is probably a problem for younger generations. Thank you very much.
Thank you, Fedor, for a nice talk. Are there any questions? Any question?
So the same, so it doesn't matter which S matrix you have. It can be kind of spin S matrix, scalar S matrix. It's always these deformations. They always give you CDG.
Yes, yes. But yes.
And what is the behavior of the free energy as a function of the radius? I just, just maybe you can sketch it.
Normally, it's something like that. I don't know. Here, it was something like that. So it goes, and it arrives to some fixed radius. And then, like square root, and then bam, and goes this way. So there are shock waves there. And so then, the meaning of this, so that there is that to some values of radius, two energies correspond, the meaning of that is not clear at all. And there is definitely something horrible happening here. So normally we assume that this is a Hagedorn phase transition, but so I would prefer not to go into details at this point. So, but at least, so this normal picture when you go, as I said, when the theory is UV complete and you go to some fixed point, so you are happy. No, this does not work. So, and so, yes. This is yes, you're right. This is CFT. So problem goes to zero, isn't it? Yeah, probably it is. Anyway, so it is something reasonable. Yes. Page 10? Let me see. Where is my point? Okay. Yes. Oops, no, this one, yeah. Mm-hmm. Mm-hmm. Yes. 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 It is, yeah, I think it is uniquely determined, and moreover, so in this, actually, yes. That's what I'm saying. Yes, that somewhere, oh, but I'm always going the wrong way here. I don't know. So this point is, yes. That's what I'm saying. You see. So in this example, it is here. Yes. So, but more generally, so if you consider integrable field theory, so then it's hard to be as happy as here and to be able to describe all the local operators. But a part of local operators, you always can not always, but so in the cases which I know, so they, like I don't know, chiral Grosny or whatever. So you always can describe a part of them which corresponds to these Fermi nodes, and you will always have this formula here. So.
Like this.